Uh, So this is what the title of your lab is. You got a notebook? Do I have to come out there and write it for you? You should have your notebook out. You should have a new page and set this up at the top.
What does it say after TV?
There, a little more readable.
Yeah.
Okay. Now, in this lab, the objective is essentially determine rate laws, I should say numerical rate laws for solvolysis reactions of T-butyl chloride and T-butyl bromide in a 50-50 IPA H2O solvent system. IPA, of course, is isopropyl alcohol, rubbing alcohol. You know what water is, and is easy enough to prepare 50-50 solution. It is miscible in all ratios. And the background of this, in writing backgrounds, you should certainly define what you're doing. And this is a study of the kinetics of of an SN1 type reaction known as solvolysis of a T-butyl halide. Now, the solvolysis reaction, simply defined as the reaction of the solute with the solvent. That's what solvolysis means. So in the solvolysis reaction of a T-butyl halide, and X represents either the chloride or the bromide in this. So we look at T-butyl halide in an alcohol, an H2O or OH. Well, the reaction is actually between the T-butyl halide and water. The alcohol is there because the T-butyl halide is not soluble in the pure water system. It'll separate. It's oil and water kind of thing. So by making a binary solvent, then the T-butyl halide becomes miscible in that, or soluble in that system, and then reacts homogeneously and uniformly in that solution. Well, what happens is because water will break into hydronium ions and hydroxides like that. What happens is the hydroxide will bond to the butyl structure more readily than the halide will. And so since the OH bonds in there faster than the halide does, it will replace it. It's called, X is a leaving group is what it's referred to. And this goes to T-butyl alcohol. And that X comes out and hooks up with the remaining hydrogen in a HX. Well, this will be a strong acid and can be monitored. Its evolution can be monitored using a pH system. Now, examining the reaction, if we can determine the rate at which the HX is formed, we will know how fast the T-butyl halide is going away. And so, because they are a 1-to-1 reaction ratio. So in the process of looking at the rate of reaction as a function of concentration, that's what we're going to do. We're going to start out with a concentration 1 and see what the rate is of HX generation. And then we're going to double that concentration and see what the rate is, and then triple that concentration. That's where I showed you earlier it was a 1, 2, 3 mil addition. And you'll translate that into moles per liter, moles per liter per second, and so forth, which we're fixing to do right now in that example. A T-butyl halide, just to give you that structure, looks like this from a chemical standpoint, structural standpoint. That's a chloride. I'm just put the halogen in there like that. And X is equal to a chloride or a bromide. So, and what you need to do is go online, look up the SDS, as they call it now. And, you know, it's not a dangerous chemical, but it is an organic halide and can be carcinogenic in its content. So what you want to do is certainly wear, I've got rubber gloves and whatever protective gear you need in the lab. And it's not going to be that complicated to use. You're going to be using very small quantities anyway as we go through this. Well, the mechanism of the SN1 reaction is as follows. It goes in two parts. The T-butyl halide, when it's placed into the water solution, step 1 in the mechanism, it ionizes, is the ionization, and goes to T-butyl cation plus the halide coming off as a negative ion. It is then step 2, then the T-butyl cation then interacts with the hydroxide from the water ionization that we showed you back up here and produces the T-butyl alcohol, and then the hydrogen hooks up with the X and we get the HX right there. It is a two-step reaction process. Now, the significance of what you're looking for in the chemistry of this, and this is, we're studying chemistry, not just pouring A into B. Anybody can do that. But if you have a let me draw it out this way. T-butyl halide, let me put it chloride, and you're comparing that to a T-butyl bromide. The study that you're doing depends on the ionization of that bond. You have to break that bond. See there, it's coming off in this step, in that first step. So who in this collection between those two will break the easiest? Okay? And so what that translates to is you're looking for the reagent, the compound that will give you the fastest K value in this. So once you determine what the rate constant is, it will go faster. The faster one will undergo ionization to that T-butyl cation faster than the other one will. And that's called the rate determining step. In reaction kinetics. You can visualize this using the transition state diagrams, the potential energy curves. If you have if you're comparing two ionizations, one from a chloride and one from bromide, I'm not telling you which one yet, what you will actually see is two mounds in the curve. It is overall exothermic, but you'll see this, and then the second step will do that. Like that. Now, if this is, say, compound 1, all right, let's say the compound 2 is faster ionization, okay? Would you say it would be easier to break that ionization, break that bond, or harder to break that bond? Be easier. If it's faster, it comes apart easier, okay? And it's going to deliver more bromide or acid into the solution, okay? So it will have a lower activation energy in there. So from this, what you would see in compound number 2, if it was going faster, actually you would see a lower activation energy. Now the second step is still ionization of the attachment of the hydroxide. And so it would merge on that end. But this would be the faster reaction with a lower activation energy. It ionizes easier. So what you're looking for is a comparison between those K values. The larger K value, it'll be a number, will be the one that ionizes easier. And you can say simply that that bond, the faster one, is a weaker bond than the one that's going slower. So you're trying to not just get a set of data that you have absolutely no interpretive understanding of. You're trying to take that data and the outcomes of that data and come up with a conclusion about the chemistry of what you're studying. And that's the ionization or breaking bonds and making bonds in the process of chemical reactions. And that's what you're studying. And when you study a kinetics of any reaction, that's the way you approach it. You look for some mechanism out of that reaction that will define how that system breaks, whether it be a complex biomolecule or a simple, easy to measure halide like this. You're looking for some way to monitor the breaking and the generation of something else. And once you understand that, then you can define the nature of the compound and how it forms new compounds. Okay. This is reaction. Okay. So simply put, what are we doing? We're taking a T-butyl halide, what I drew a picture of a minute ago, and throwing it into an alcohol water mix. Can you see that in your mind? Okay, so it's T-butyl halide that's going into H2O and an IPA and going to T-butyl hydroxide plus HX. There's our reaction. Now, what did I tell you in writing a rate law? It's always in terms of the reactants, right? So it's the product of the concentration of reactants raised to the orders of reaction, which are X and Y in this case. We don't know what it is. That's the objective of the experiment, is to determine those orders of reaction, and the rate constant goes with it. So I'm going to write the rate law is equal to K for this reaction. The rate, whether it's chloride or bromide, that's what you'll define it at that time, is times the concentration of the T-butyl halide times the water. Those are the two reactants in this. And we'll go X and Y. So there's your empirical rate law. And our job is to determine what X and Y are. Now, to simplify everything, make it doable, the Y here, or the order of reaction with respect to Y, will be given. And it turns out to be a zero order reaction. So if the exponent on the whatever you put here is 0, what is this term? Goes to 1 automatically. So if the order of reaction of water is 0 given, you don't have to go through an experimental to determine that, then the equation, the rate law that you're using is simply this. And you need to define X and K. Are we still with me? Now all this boils down to is you'll have the T-butyl halide added into a solution of IPA and H2O is what you're doing. And you'll have a pH electrode that you'll measure because it's going to be generating the acid. And the amount of acid that's generated is equal to the amount of T-butyl halide that goes away. Everybody good? Can you see through this? Hopefully. Well, after we do a few, you'll hopefully get the idea. Now, this is an exponential equation. And so in this form, you cannot solve the problem. So what is typically done when you have an exponential is converted to a linear equation. To do that, you take the logarithm of both sides. That's the common procedure. And this is a unique procedure, but here you take ln of the rate and then the logarithm of the right side. So if you take the right side, then you have a product right here, k ln to the power x. So that translates to x ln of T-butyl halide. If you don't remember your algebra, that's fine, because this is the equation. It's not going to change. There's no variations in this. And I'll show you the outcome of this, plus ln of k. You add exponents when you're working with exponents, multiplying exponents together. This equation right here is in linear form of the form y equals mx plus the y-intercept b, right here. So you can, I'm showing you that it can be converted to a linear function. And so that's what your object is in this experiment, is to get the x and y out of this, plot them on 2 dimensions. You go online, you'll see that plot page on there, and determine whatever the slope is. Once you get that slope, you'll have the order of the reaction. Then once you get the order of reaction, you go back in and get the K value. Like that. This equation actually, in the data generated, will show up in this negative quadrant, where you will have ln, see this is the x value, ln of concentration changes, and ln of rate on the y-axis, like that. And you will have, I'm fixing to show you how to do it, a line there. Actually, you'll pick 3. You'll have 3 lines that will converge at that point, at one of the points on here, like that. This will be, say, at 3 time points, time 1, time 2, and say time 3 out of the curve. Now, the reason I drew this right here is this point, once you converge those through that point, this is at this point. Now, don't misinterpret me on this. This is a 0 value for ln of concentration. It is not a 0 concentration. I didn't say that. I said the 0 value is for the ln of the T-butyl halide value. It's 0 at that point. And whatever number you get there can be applied into the equation that we defined. And it's easy to get the K value then, because, look at this right here in the equation, the ln of T-butyl halide becomes 0. And so this whole term goes away. And all you have left is ln of rate equals ln of K at that point. And you solve for K to equal e to, and it'll be in the negative quadrant. So it'll be e to the minus ln of whatever rate you get at that point. And that will be your K value. And you'll do that for the T-butyl halide and T-butyl bromide. This is a big boy experiment. And requires several steps. And you can keep up with what's going on. Now, what is measured in this experimental measurements? Now, the object is to run 3 experiments and determine rate. Yes? Yep. So, in the work we just finished, we've done this. We've done a problem. You know how to work problems like this now. Yeah. Okay. You go in here and hold one constant. See, you hold one constant and vary. And what do? You look at the change, don't you? Is that what you did? Don't get confused on me, because this is, I'm trying to teach you this. This is what you're going to do. You're going to set up one of these, and you're fixing to measure that. How are you going to do that? You need to start out with experiment 1, 2, 3, and you're not going to have 2 components. You're only going to have one, which is the T-butyl halide. and you're going to have concentration 1, concentration 2, and concentration 3, and you're going to look over here and see what happens. That's how you deal with this lab. I'll be there to remind you. So, in set up your raw data, if you want to put it in like that, what's the first thing you're going to need? Test 1, 2, and 3. Now you decide on, well, I got to put in concentrations of my T-butyl halide. Now I showed you that earlier in my previous class. And what did I do? I took a 2 ml sample, and I think I put same volume in both of them. But I take 1 ml, 2 ml, 3 ml. I'm adding 3 different concentrations. So it's volume of the T-butyl halide added. Well, simple enough. You'll squirt 1 milliliter into a given volume of IPA water. Remember? You'll have a pH electrode in there. And what will you see? Well, you'll see a trend. It'll come out like this, and that will be number 1. I'm going to move it up a little higher just to emphasize the issue. Because that's a pH versus time. So when you inject that 1 mil into that beaker, and you've got the pH electrode sitting there, it's going to activate pH values in real time. Then you'll clean up and you'll have beaker number 2, and you'll inject a 2 mil sample. You'll increase the concentration. You'll double the concentration, because we want to see what doubling concentration does. And it generates the second curve. And you'll find out, let's say it comes down through here, like that. And then you will do the third concentration. You'll set it up again. You'll have a third set up. Say you start with 50 mils of the IPA water, and you'll put in 3 mils this time. See what happens. See what the trends are. So in that one, we get a third curve. 1 mil, 2 mils, and 3 mils. That's the kind of data you're going to get out of this. Well, out of that, you have to get a rate of reaction. How do you do that? Well, it's in terms of pH as a function of time. So if what you'll do, now this you have, I don't want to confuse you. You have the equation rate equals, ln of rate equals K-ln of concentration plus ln of K. And you're looking for these two. So that means you need a concentration and a rate. This term right here is your X, and this term, ln of rate, actually, is Y. From this 1 mil, you'll be given the density of the T-butyl chloride. And then you get grams. You can't convert grams to moles. And you'll convert moles, you'll have that many moles of T-butyl halide in so much volume, moles per liter. So you'll have a concentration. And so this will give you the concentrations of T-butyl halide in moles per liter. Based on the density, you convert volume to density. Density times volume, grams per milliliter gives you grams, and then you convert grams to moles, and moles and how much you put it, the mix is. If you put in 1 mil, that's going to be 51 mils. And so you have to divide by 0.051. I'll be there to show you. It's on the worksheet. I'll show it to you in a minute. Okay, so what you have is these three, and then from that, once you get those concentrations, then you'll have an Ln of T-butyl halide. Those three numbers are your actually your X values that you'll plot. Okay, so what does that translate? What does it look like? Okay. In experiment 1, in this particular one, we injected 1 mil. Well, the in T-butyl chloride is 0.85 grams per mil, so that's 0.85 grams. When you divide that by formula weight, this is your moles of T-butyl chloride right here. And then you injected it into 50 mils, so that'd be that many moles per 0.51 liters. And so that would be your concentration. Then you take the Ln, see up here, Ln, which is in that equation that we had over here. You will have that X term, and that's what that's about. And so that will be your X plot. And that'll be, and I've got it over here, X1. And then you inject 2 mils. Now this will be, this table right here is good for all of the experiments. So you can put this table into your notebook as XY, as all your exponents. X values are already done for you. But this one down here is what you need for your Y values, your Ln of rate numbers here in moles per liter second. Okay, so in experiment 1, you, at 100 seconds, you found this to be your pH trend. So what you'll do is after you generate these three curves, is you'll put the interpolation line in and you'll slide it along, and it'll tell you what the time is in the box. This one shows 100 seconds. The 1 mil injection was 2.588. The 2 mil injection was 2.358, and then we have a 2.258. Now, you increase concentration, you decrease pH. That means more acid is generated. Now, to calculate, change pH into hydronium ions, and hydronium ions is the T-butyl halide consumption, is 10 to the minus pH. Right here. When you bring this down, when you download this, use this as a model. Because see, you're going to generate the curve and pick a time. Actually, you pick 3 times. Pick a time. This just shows 1. Pick a time. And you'll have 3 pH values. And then you'll take 10 to the minus, this number in here, 2.77 times 10 to the minus 3 molar, that's your molar concentration of your acid. That's 10 to the minus 2.588. This number is 10 to the minus 2.358 right there. That's that second one in here. That's the second curve at that 100. I mean, this thing will split those out pretty closely. And then the 3 mil injection would be the 10 to the whatever 2.258. That's that one. Well, that's the same as the T-butyl halide, so I'm just carrying it across. And this is your hydrogen generated per 100 seconds, so I divide that number, concentration, by rate. So this is like miles per hour, except we use moles per hour, molar per hour, or seconds. And I've got a rate now, and then I take the Ln, and those are the numbers you plot. And so we have an X, see these came down here, and these right here are down here. And so I plotted these, X against Y. And I got this number right here is where it intercepts. And I'll show you how to, the Vernier will, well, the Excel program, if you use that, will automatically plot, give you the equation. And this is your Y-intercept right here. And so the y-intercept is what that number is, where that runs into this axis right here. And so this is K equals e to the minus 9.7664 for this experiment. K value. Because this is your ln of K. And to get the K, you have to take the analog. Now study this. That's why I gave it to you. And because you're going to set up a beaker, and you're going to inject 1 mil, and then set up a second beaker and inject 2 mils, set up a third beaker and inject 3. And you're going to generate this kind of curve. And you're going to do it for bromide and chloride. Actually, I'm going to split the lab into 2. Half of you are going to do the chloride, and half of you are going to do the bromide and swap data. That'll save us all a lot of. But this is a very, very sensitive experiment. Now, some of the cautions in this experiment include, of course, you want to be careful with all the chemicals, okay, and in using them. Wear rubber gloves and eyewear and what have you. But all of your beakers and all of the equipment that you're going to use needs to be neutralized using the buffer systems and what have you. It just occurred to me. And so that you won't have any contaminations. Because when you start this, you want to start them all at the same pH, so that when you get your numbers down here, they're in the relatively same positions, where they should be, 1, 2, and 3 mil injections. If they don't start at the same point, you have to put in a correction factor, whatever that starting differential is. Now, I'll show you how to do that if you have to. But hopefully you can figure out how to start them all at the same pH. Now, it just occurred to me. Okay, now let's start this.